Hi, everyone. This is Charles Hoskinson broadcasting live from warm, sunny Colorado. Always warm, always sunny, sometimes Colorado. I didn't have time yesterday, but I have a little bit of time in my schedule today. Before I go home, I wanted to talk a little bit about proof of work versus proof of stake. And actually, this video is made for Jack Dorsey. So yesterday, Jack said, proof of work is better than proof of stake because proof of work is less centralized and more secure. This is a common thing that people that are indoctrinated in the school of Bitcoin tend to say, and it's a bizarre thing. Normally, most people, laymen, don't have strong opinions on consensus protocols in computer science. It's kind of like saying, what is your favorite surgical procedure or method to stitch up a patient? If you're a surgeon, you'll probably have a way of going about that and an opinion. But if you're a layman, you'd be like, I have no idea. I don't know. I like cholecystectomies or something like that. Who knows? And so what's happened though is because everybody wants to be an expert, everybody wants to talk about these things. What we've had is this unfortunate conversation, which is really difficult to actually converge to anything meaningful. And the purpose of this video is to kind of talk a little bit about how to think about these things. And if you're actually curious of doing the hard work of developing a good opinion, I'm going to give you guys some great resources specifically for that. So let me go ahead and share my screen. And there we go. Okay, so the first thing to look at is this lovely paper from Leslie Lamport. And actually, this is one of the most famous papers in computer science, Times, Clocks, and the Ordering of Events in Distributed Systems. And Leslie published this back in, I think it was the 1970s. And it has about 12,000 citations. It's one of the most cited papers in the history of computer science. And this paper really outlines kind of a difficult problem, and it discusses ways you go about thinking about it and solving it. So ordinarily, when you're just a single person and you're observing something, so let's say that you're Alice. Okay. And we'll give her a nice little dress. And you see an event, and we'll call that event A, and then you see event B. Okay. And this is occurring in a local setting. Alice can order these and say, oh, okay, well, event A happened first and then event B. All right. But the problem is when you start introducing more actors, like right here's Bob, and he's witnessing it. And from Bob's perspective, looking at it, he saw event B first. So that happened first. And then he saw event A. So that happened second. So the question is, who's right? Is it Bob or is it Alice? It's a really interesting question, and Lamport actually discusses this amongst other concepts, and he calls it kind of a partial ordering, and there's all kinds of things that have come from here. And it's actually created a beautiful, lovely field of computer science called distributed systems, and for this work and other work, Lamport was awarded the Nobel Prize in Computer Science, the Turing Award. And he's a lovely guy. He recently spoke at our internal seminar, and we had a chance to talk about TLA amongst other things. I was trying to goad him into talking about clocks and Paxos, and he's like, oh, I don't do that anymore. I do a TLA now. And if you're really curious and you really want to learn all these principles, first you kind of have to learn these types of things running on a single computer. Then you go to the next level up, which is a collection of computers that are in different locations. And I have two wonderful resources for you guys. First, a series of lectures out of MIT. It's MIT 6.824, the Distributed Systems class. And it covers introduction, RPC and threads, GFC and replication, and Go and threads and so forth, all the way down. And it actually eventually talks about Bitcoin at the very end. And then there's another series of lectures from Martin Kleppmann over at University of Cambridge. And these cover all kinds of cool topics as well. And it's an 8-part lecture series. So I'd recommend both of these very highly. They're not for the layman. You have to kind of have a pretty good programming background and understanding computer science to be able to make the best out of it. But the point is, this is a topic unto itself, and it's something, that's why I mentioned the surgery situation. It's something you really have to have a lot of knowledge to start developing a strong opinion about certain things. But in general, when you talk about these types of problems, the first thing that you do is you try to work on definitions and foundations. And one of the things that our scientists did, they wrote a lovely paper which actually has about 1,100 citations. And this is the GKL paper. Its formal name is the Bitcoin Backbone Protocol Analysis and Applications. And this has been cited as much as pretty much any other crypto paper 1,100 times. It's a very famous paper. It's by Juan Garay, who's at Texas A&M, and two IOHK alums, Agalos, our chief scientist, and Nikol Arenardis, who is running the University of Athens lab with others. And basically what this paper does is it tries to create definitions and foundations. So it creates some foundational functions, this concept of a content validation predicate, an input contribution function, and so forth. And it gives you a way of talking about a cryptocurrency protocol. And so then you get properties out of it, and two in particular, the common prefix property and the chain quality property. And what this is really nice is it's a theoretical foundation, and you can prove all kinds of interesting and nice properties about this foundation. But then once you have that, what you can do is develop what's called a security model. Okay. So what a security model does is it says, all right, I have some sort of adversary, and he's evil. So give him a little monocle and a top hat and a cane. And the adversary basically is always trying to break things. And what your security model basically tells you is when they're going to win and when they're going to lose. Okay, so what attacks are you defending against and what attacks are you not defending against? And that's always connected to the capabilities of the adversary. Okay, so your capabilities, for example, do they have a classical computer? Do they have access to your computer? Can they eavesdrop on the communication medium and collect messages? Or maybe they have a quantum computer. Okay. So oftentimes you'll hear things like cryptocurrencies are not secure against quantum computers. What they're basically saying is if your adversary has a quantum computer capability, then the security model may not hold and the adversary may be able to win. And this is what cryptographers think about when they're modeling and building protocols. So there's plenty of protocols that allow you to sort out orders and decide when events have happened, your transaction or my transaction, and basically be the engine of a distributed system. So in the case of cryptocurrencies, you have to move from one block to another block. And those protocols may be what are called Byzantine fault tolerant or non-Byzantine fault tolerance. They might not be able to admit Byzantine actors. In other words, can you have an adversary in your system, and will the presence of that adversary break the system or not? So here's an example of a non-Byzantine fault tolerant, very simplistic protocol. Let's say you have a set of 7 people. And what you do is you say, oh, okay, we're going to pick from this set of 7 people who gets to be in charge and make a block for our blockchain. And what we're going to do is have a random number generator and have each and every one of them run a random number generator. And whichever one is the minimum, that's going to be the winner for that round. Okay. And actually, Intel did do this. This is, I think, a proof of elapsed time or something like that for something called Sawtooth. Now, on normal computers, this is actually not a secure algorithm, because what I can do is I can just hijack my random number generator, and let's say it returns something from 0 to 1. I can just hijack my random number generator and say, all right, just always return 0, which means I always win because everybody else will have a value equal to or greater than mine. Okay, so that does not admit a Byzantine actor. Sawtooth does, because the random number generator actually runs on SGX. So you can't modify the code. Now, this is an example. So there's a lot of nuances and elegance to how these protocols are developed, but you always, whenever you're developing a protocol, even proof of work, implicitly or explicitly, you need some notion of a definition and you need to create some sort of security foundations. It was unfortunate that Satoshi did not do that. It was a brilliant and inspired protocol based on Hashcash proof of work, but it took years for cryptographers to get around to retroactively building a foundational model to kind of understand what happened with Nakamoto proof of work. And actually, it turns out that there's a lot of nice security properties of proof of work. And let's talk about that. So really, when you think about a cryptocurrency protocol and a blockchain, you have three things that happen. First, you have to pick someone to make a block. Okay, that's step one. And then two, you need to go ahead and make the block and distribute it. Make and push to the network. And then three, the network has to accept the work. All right. So all the energy consumption of Bitcoin occurs here in the picking part to make a block. So what happens is you have this proof of work that people do, and they're basically buying like computational lottery tickets. And if you get a magic number, you hit a magic value that's below some target, then you have a valid block. Okay. And this is an egalitarian meritocratic process, and it's an external resource. So mining is not incumbent within Bitcoin. It's an external thing. I have to have an external miner. I have to have an ASIC to basically do this process competitively. And I can either do it solo, or I can do it with a private pool with just many ASICs together, or I can do it with a distributed pool where I actually contribute with some sort of work unit and so forth. Now, proof of stake and proof of work are functionally identical on these two sides. Number two and number three. So PoS does this, proof of work does this. You make and push blocks. You do it the same way. You could take a proof of stake algorithm and plop it on top of Bitcoin's system. And for the most part, it's going to be that way with some implementation detail differences. And then you're going to have validation rules, ledger rules, and acceptance rules for whether those blocks look good or not. So the easiest way of thinking about this conceptually is kind of like a poker game. Somebody has to be the dealer who shuffles the deck and deals out the cards. Step two is the dealing of the cards. Step one is picking the dealer. And step three is you picking up the deck and looking at it and looking at those cards. And what that effectively does is you have five aces. If you have the information card, a joker, you'd say, well, hang on a second here. This is not a valid hand. And so the question is, can you do a complete validation or a partial validation or a blind validation? What level of validity can you have with the way the blocks are made? So various consensus algorithms and ledger rules in the cryptocurrency space, because there's many of them, have different levels of things. In the case of Bitcoin, it attempts to be a completely trustless system. So when you receive that block, you can check the proof of work, you can check the contents of the block, and you'll have an entire collection of the history. You're able to validate, assuming honest majority, that block is real and legitimate, and not going to be rolled back. So it's a very powerful deterministic system, and that's actually quite rare to have with complete decentralization. It's why Bitcoin is so great. But that first step, that collection of magic value, as I mentioned, is where all of the energy consumption occurs. 99.999997% of all the energy occurs there. And basically what proof of stake does is it says, okay, let's invent some sort of synthetic resource. So mining capabilities, ASICs, are a resource. That's the way to think about them. And for any given time period, there's going to be some set of all ASICs. So if you can union that whole set of ASICs and add them all together, this right here is the total pool of resource. And when you think about a synthetic resource, basically what you're doing is saying, oh, okay, well, if I have 25%, let me zoom up here, of the ASICs, on average, I should be able to find those magic numbers 25% of the time. So if I have 25% of this synthetic resource, on average, my expected value should be 25% of the time. I get to be the dealer. I get to be that person who gets to make the block. And then I can go make the block and push it. And of course, if it's accepted, I get paid for that profit. Okay. So the question is, the distribution of this synthetic resource, is it fair? And also, is it secure? Okay. So you need a security model against an adversary to even be able to have a meaningful discussion, which is why this paper is so incredibly important, because you can then have a very rigorous conversation about what security properties does proof of work provide. And then if you're going to create a synthetic resource and build a different type of system, what security properties does that system have? And we wrote that paper. So this paper, Ouroboros, originally came out in 2017, but it was updated in 2019 to reflect all kinds of new, cool, interesting things that were gathered. And this is built with that GKA model. So basically, what the paper does is it talks about the design challenges of a proof of stake. And really, they're saying, okay, how do I get that synthetic resource to work properly? And how do I use that synthetic resource to correctly pick a collection of people to make those blocks? And you, of course, have to model this, and you have to create rigorous security proofs for these types of things. And so, you go down and you can actually take a look at the entire model, and it talks about time and synchrony. Where have we seen that before? Well, here we go, 1978, Lamport stuff. We probably even cite Lamport's paper. Wouldn't surprise me in this paper. Everybody does. It's how academia works. And then it talks about liveness properties and all those things, honest chain growth, existential chain quality, and the common prefix from GKL. And what it does is it over time builds up a big security model. It kind of discusses that if you use this under the assumptions that are inside this paper, that basically you'll have equivalent security to the proof of work security. Now, the problem is we're using that term assumption. It is the most dangerous term in all of computer science, that and ideal functionality. Those are the two. And those assumptions basically says that this evil adversary we have here can only be defeated under the model and the assumptions that we've made for defeating him. And just because we have a peer-reviewed paper doesn't mean that there's guaranteed security against all types of adversaries and all types of conditions. For example, the computers that are talking to each other, there's different communication models. So when you send a signal between the computers, you can have them all occur in a synchronous time, or they could occur in a partially synchronous time, or they can be asynchronous. And there's a very cool thing called the Fisher-Lynch-Patterson impossibility result that actually talks about some fundamental limitations if your system is asynchronous versus synchronous or partially synchronous or so forth, about the level of security that you can have. And that's just how messages are passed. Another thing is how many Byzantine actors can you have in your system? Is it a third? That's very common for sharded protocols and asynchronous systems. Is it a fourth? Is it 50%? And it turns out actually Bitcoin has a lot of really amazing properties with proof of work. For example, you have the ability to recover from attacks. So let's say that there's a attack on the system. Over time, an honest minority can, if they stick around and keep mining, and the attacker stops, the minority chain can undo the majority chain, and we can recover. So there's a disaster recovery mechanism that is within proof of work. Proof of work mostly is partially synchronous or asynchronous, depending upon who you ask. This is a bugbear of a few people in the space, like Andrew Miller. And that means that it can operate in very uncomfortable network conditions. You don't know ahead of time who's going to find that magic value. That's not necessarily the case in a lot of consensus algorithms. A lot of consensus algorithms, you know who the next person is going to be to make that block. It's like knowing who the next dealer is going to be. So you can go and coerce or attack that dealer. In Bitcoin, it's not predictable. In addition to that, Bitcoin actually generates a pretty reasonable source of randomness. It's not perfect, and it's subject to grinding attacks, but you get a reasonable supply of that. So you have a lot of great security properties in addition to a 50%, so 1/2 Byzantine resistance. And so to replicate those for proof of stake is non-trivial. You have to come up with creative new ways of getting sources of randomness. be able to make the selection of people fair. You have to be able to recover from 51% attacks. You have to be able to have a proper clock for the system. And usually what people do is they inherit that clock from a system like NTP to synchronize things. But there's actually ways to get around that and actually create clock from within the system. We wrote a paper called Chronos specifically for that. So a lot of people ask, why do we have so many Ouroboros papers? And the reason we have so many Ouroboros papers is that a lot of those properties were not solved in this paper right here, the original Ouroboros paper. If you actually go to ePrint, which is an IACR ePrint, which is the kind of the cryptography archive for most academic work in the domain of cryptography, and you go ahead and enter in Agalos. He's our chief scientist. You'll see a lot of the papers that he's written recently. He's an extremely verbose academic. But actually, let's enter the keyword Ouroboros. There we go. And you'll see how many different Ouroboros papers, Ouroboros, so PoW and a universally composable time model. We got Ouroboros Chronos, which is the decoupled clock. Cryptsina says how to preserve privacy. Ouroboros BFT is a piggyback protocol to help with side chains and federated protocols. Genesis allows you to bootstrap from Genesis. That's another great security property of proof of work style systems. You never have to have a checkpoint. You can just redo the proof of work and you check it all the way from the chain you're giving, and you're able to have proper chain selection. PoW puts adaptive security and moves it to a semi-synchronous model. And actually, you're not done, because there's other papers, like, for example, Ledger Redux is one. And Ledger Redux talks about recovery from 51% attacks, consensus Redux, excuse me, and also recovery from, and also fast finality and things like that. So it says in this work, we talk thorough treatment of self-healing properties of proof of work and proof of stake and so forth. So there's a lot to this, and it's a very, very complicated thing. But, the easiest way I think of thinking about this in general is like an engine. And when you have an engine, the engine has this concept of throughput. Okay, this engine has this concept of your latency. How long does it take to deliver the power? How much power can you deliver? And kind of a capacity notion. And proof of work is a type of engine. It's the thing that runs the Bitcoin blockchain and other blockchains like Ethereum. And basically it says, okay, you can get a certain amount of work done with every block over a certain amount of time. So the distance between these blocks can be 10 minutes. It can be 10 seconds. Okay. So it can be some value time T. It's your latency consideration. And capacity is, how much can I put in those blocks, And so proof of stake is just another type of engine, and it has a throughput and a latency and a capacity concept, and also there's all kinds of other things. Like if you have a synthetic resource, you can have N synthetic resources. So right now in Cardano, your synthetic resource is ADA, but you could include an arbitrary amount of other tokens and create some sort of weighting between them. And perhaps one is more merit-based instead of just plutocratic. With proof of work, every resource that you put in requires physical hardware. And so that means that that resource tends to monopolize itself. And you tend to have a situation where you have a race to centralization. You go from many machines to just a few, a much smaller set, because the smaller set has an economy of scale, usually subsidized power and first access to ASICs or patented hardware that's not easy to replicate and get into market. And that's why people often say there's only a small set of miners. There's less than 10 major mining operations control more than 50% of Bitcoin's resource. With a synthetic resource, you can move it instantly anywhere in the world. And also you can have multiple synthetic resources. Okay. And you can weight them accordingly. So already that's a much better property of the engine. And because this is a gargantuan computational task, it's very expensive. These two things suffer as a consequence. You first have to use a lot of energy, a lot of cost, and a lot of resources, real life resources for that. If this is cheap, then you have overall more energy for your system, more power, other things to actually start accelerating these guys. And you also can optimize latency and capacity and so forth. As a consequence, proof of stake systems actually tend to be much faster, and they also tend to be able, and faster in terms of block time, and they also tend to be able to have a much higher throughput, higher TPS. Now, the other thing is because your selection algorithm to pick all of these people can be done ahead of time, there's a lot of advantages, theoretical and practical, to knowing what your leader schedule is going to be. And you can obfuscate that so that an outsider doesn't know, but the individual does know. So you end up getting much more efficient utilization of resources and a lot more optimization of resources. And in a practice, this actually creates, in a proof of stake system, usually a heterogeneous network. Okay, the heterogeneous means that there are different actors, there's specialization. So we start as single cell organisms, but evolution says, hang on a second here. Differentiation and specialization actually allows you to have brains and eyes and other body parts. So similarly, you can start as a homogeneous network, but when you start actually creating heterogeneity in an effective way, you can develop different organs, and that specialization allows you to optimize and create economy of scale. That's why proof of stake tends to be better. The other thing is that proof of stake from a security viewpoint is an endogenous system. Endogenous. So instead of exogenous, outside, endogenous, inside, you have internal security. When you look at a proof of work system, the problem with proof of work, and one of the security challenges, is it doesn't like nearest neighbors. What I mean by that is if you have two proof of work systems, proof of work 1 and proof of work 2, and they use the same algorithm, okay? All right, algo alpha. If you have an external actor comes in who has enough hash power to perform a 51% attack, what that actor's incentive is to destroy one of the chains. This is called a Goldfinger attack. Short sell, make profit because the chain is unusable and confidence in the chain is lost, and then switch the mining power over to the other chain, assuming that the market price of these two chains is roughly equivalent. Okay, so let's say this is Zcash and this is ETC. So I think they use the same mining algorithm, and I'd have to look it up, but I believe they do. So let's say you have enough to actually perform a 51% attack on one, and for a time, both their market caps are relatively comparable. It makes sense to go 51% attack, destroy the market value, make some money, and then after you've made the money, just simply mine the other thing. You get to reuse all the mining equipment, and your identity is usually anonymous in these types of things. So nobody even knows you're the one who did it. And you can kind of get away with it. This is why proof of work tends to be maximalist and winner takes all. Proof of work only really works when you don't have nearest neighbors. You have one coin that's up here with tons of hash power, and everything else is kind of down here. And that's actually where Bitcoin is at right now. And that's why Bitcoin works so well at the moment. Proof of stake doesn't care at all about that. Polkadot shares a very similar consensus algorithm to Cardano, and Cardano and Polkadot are relatively comparable for the most part in price. Some days they're up and some days we're not up. But that doesn't mean anything to our security because the security is not external, it's internal. The security comes from people who are vested inside the system. And you can actually quantify the dollar value of the security. It's hard to know how many miners are out there and what the value of all those things are and actually how much people paid for things. But you sure as hell can know the token price of a proof of stake system. Now, it's not perfect, and there's actually a lovely paper that some of our people wrote, and it's called Cryptocurrency Egalitarianism, a Quantitative Approach. And it kind of discusses the concept of ASIC resistance in proof of work systems, but actually curiously and nice and fun, says our simulations show, as expected, that ASIC resistance increases a cryptocurrency's egalitarianism, which means it's more equal in its distribution of participation. We also measure the egalitarianism of proof of stake based protocol, in particular Auroboros, and a hybrid proof of stake, proof of work cryptocurrency, Decred. And we show that stake based cryptocurrencies under correct selected parameters can be perfectly egalitarian, perhaps contradicting folklore belief. So it's a really cool paper, and highly recommend you guys read it and look at it and think about it. But the thing you should take away from this entire conversation is there's no silver bullet. There's no notion of proof of work better than proof of stake, or proof of stake better than proof of work. It really depends upon your adversary and the security assumptions and the capabilities that you care about, your network structure and what you value, heterogeneity. Do you value external security, or do you want security coupled and connected internally to the network? What are your performance requirements and so forth? How expensive do you want to make an attack be? Are you worried about Goldfinger attacks or these types of things where chains have nearest neighbors and so forth? And also, the other thing you should take away from this is that proof of stake is ridiculously hard in practice. You have to know a lot about time. You have to know a lot about random number generation, VRFs, or other types of protocols or things like that. You have to really think carefully about recovery models. Is it okay to have a checkpoint? Do you not want to have a checkpoint, and so forth? Your network assumptions. Is it a synchronized network? Is it not a synchronized network? The more pristine things are with your assumptions, like, for example, a fixed quorum and in a synchronized network, the higher the performance can be. But it's a glass cannon, and it's very brittle. The more disastrous your assumptions are, as you go from synchronous to asynchronous and a fixed to a floating committee, and the more egalitarian your selection mechanisms are, generally that hurts your performance inside your system. And this is a super well-studied problem. And if you actually take the time to go through these two collections of courses, you'll actually understand in practice how remarkably intricate and beautiful this particular space is. So I just wanted to make this video to try to sort fact from fiction and let you guys know where these things sit. I'm really proud of the research that's been done with Auroboros. I mean, if you look at these are not easy papers to write. Um, if you actually go through them and spend time with them, this wasn't just some babble. There was a huge amount of deep thought and very precise language. Every single one of these things were reviewed time and again, and external people looked at them, and they said sometimes very harsh things. And you have to be intellectually honest with these types of papers. Like when you go to the Ouroboros original paper, let's find it for you guys. I might have moved it, but actually, if you Google it, Ouroboros, right? Cited 980 times. If you actually go in it, you'll notice something. It says previous work, and also it'll give credence to related and follow-up work. So, for example, you look through, it mentions Fruit Chain and mentions Algorand and all these other things. And actually, if you go to the Algorand paper, so 31 here, let's go to the citations. Yeah, Sylvia Macaulay, Algorand. You'll notice something. The paper actually cites, if you go Megalos, Chias. Other paper close to us, Ouroboros, a proofly secure proof of stake protocol. And it actually cites us. And right there is the citation there. And that's just how academia works. There's so much tribalism and brutal competition that exists inside the cryptocurrency space. But in the academic world, this is just best practice. Everybody knows each other. They talk about each other. They learn from each other, and they piggyback. There are some really cool and interesting and fun things in the Algorand paper that Macaulay put together. And Macaulay is another one of those guys who got the Nobel Prize of Computer Science. He's one of the smartest guys in the entire cryptocurrency space. And it's just extraordinary that he's decided to honor this industry by being in the industry. And Macaulay's work stands for itself. And similarly, the work that's done here stands for itself by the citation count and the fact that it was accepted through the peer review process. And this doesn't make a product. The product is everything else. It's the collection of assumptions, economic assumptions, the social dynamics inside the system, and what that engine actually does. When we talk about throughput, not all transactions are created equally. Okay, so a transaction on Bitcoin is a very specific thing. A transaction on Ethereum is a very, very different thing. Okay, one is a general purpose computer, the other one is not. If you think about Ethereum or Cardano or any of these systems that aspire to have or do have smart contracts, uh, basically you could be talking about a Uniswap transaction. You could be talking about purchasing a Cryptokitties. You can be talking about running and executing some sort of decentralized Uber. All Bitcoin can do is move a Bitcoin from one location to another location, one address to another address, and it carries with it some crypto capabilities so you can build layer 2 infrastructure and some metadata capabilities so you can embed some metadata. But transactions in themselves are incredibly rich. There's actually 5 properties of them, 4 to the transaction and 1 meta property. You have assets that runs on the rail. You have identity, so those are the people behind it. You have metadata that runs with it. So for everything from the timestamp to why you're doing the transaction and so forth, the contractual construction, and then the jurisdiction, so the geographies and law, the legal component. Okay, so Bitcoin really only moves one particular asset, says nothing about identity, limited metadata capabilities, almost nothing about contractual capabilities, and is completely blind, deaf, and dumb to the jurisdictions that it operates in. Well, this is why we built Ethereum, because it does a lot more. It actually allows you to do all those things. But to do those things with a high throughput, high capacity engine does a lot of work for every block. And, those things can happen quickly and do it low latency and be always available 99.997% of the time. Super hard. And it requires a large family of protocols. And the point of proof of stake is it gives us a much better overall engine and design and a much more egalitarian approach because you can have many synthetic resources. And then also because you've eliminated an enormously expensive step, you can now reuse all those resources towards the network's benefits. So ultimately, you can operate the network much, much, much more efficiently than you could otherwise. Now, proof of work still does have its place and purpose. And actually, there's a whole new family of proof of work protocols that are coming that make proof of work better and more efficient, like the Prism protocol that Pramod Viswanath created, and we actually contribute there as well. And there's still tons of innovation, like log-space mining was a recent paper that Dionysius Zindros and Agaloskiasis published that do deal with that. But it's a rich topic. So, Jack, the long and the short is proof of work is not equal to proof of stake. They're different engines. And to say that proof of work greater than proof of stake is really a crazy statement. That's like saying a truck is better than a Lamborghini. I have both. And I'll tell you, there's no reality that you can take your Lamborghini up to Wyoming and some of those ranches. And I would never want to take the truck, the Chevy 2500, to a track. Okay, so it all depends upon the context, the assumptions, the environment, and other such dynamics, and what you're attempting to do with the system. You want to do very useful things. For example, you want to build systems that permit for assets, identity, metadata, contractual relationships, and can automate the legal side, and you want to quantify your security internally to the system, then proof of stake is a significantly better way of doing things. If you want to do other things, then perhaps proof of work is a better way of doing things as well. But there's a very deep and elegant story here. And I hope this helps you guys kind of grok and understand this entire story and why these things are the way that they are. The problem with Bitcoin maximalists is they've become a cult. And they don't really care about evidence. It's kind of as preposterous as saying, well, the Steam engine is the best engine ever, and we will never, ever move from the Steam engine, the cult of Steam. And if somebody comes to you with a battery-powered car or really highly optimized diesel internal combustion engine, and you say, no, this is much better than the Steam engine, you can provide all this evidence about horsepower and efficiency and operating cost and the portability of the fuel source, et cetera, and they won't care because it's not about empirical evidence. And there's no burden of proof or standard that you can provide. When we started in this industry in 2015, we didn't know if proof of stake was real or not. There were a lot of people who purported that proof of stake was secure, but there was no foundation. There was no definition. There were no security models. There was no real rigorous analysis of the adversary. And it took years of research and going through the peer review process and discussing the matter with scientists all over the world, lots of prototyping, lots of competition to get to a point where we could definitively say that under certain contexts, proof of stake not only works, but is absolutely the best protocol to use. And there's a long road to add things to it. Now, that doesn't mean it's universally useful and amazing in every possible capacity and that all the research is done and that these protocols are final. But that's being humble enough to admit that the road has many steps ahead of it and the journey is very long. To say that everything that could ever be said and done in our industry was achieved in January 3rd of 2009, and that's that. It's exactly the same as the religious fanatic who throws religious doctrine at you and says, no, the earth is only 7,000 years old because this book says so. And then you show them all the evidence and they say, no, I don't believe it. God has said so. And that is the final word. And that's the only evidence that I need. So they're trading one God for another God. And that's something you should never do. You should always be having an open mind. You should always try to understand what's the context behind these things. And do understand distributed systems is a very old field of computer science. It's from the 1960s, 1970s. And people have been thinking about these things for over 5 decades. And as a consequence, there's an enormous corpus of tradition, knowledge, and best practices that exist. And everything is up to how are you using the system? Why are you using the system? And ultimately, where do you want it to go? And what do you want it to achieve? What we've accomplished with Auroboros succinctly is we run a global scale network that moves every day $10 billion or more of value for less than 6 gigawatts of power per year. Bitcoin, on the other hand, is in the hundreds of terawatts, which is comparable to an entire nation state. And it's only going to get worse as the price of Bitcoin and the use of utility of Bitcoin goes up. Okay, so on an ecological basis, proof of stake is significantly greener forever than proof of work. What we've also achieved is constructing a system that has far more people involved in the construction of blocks. And that's not just a throwaway statement. There are literally thousands of stake pool operators who are registered and delegated to and making blocks every 10, 15 seconds on the network. Just you can time your watch to it and go and see the block explorers and see them come through. And there are probably stake pool operators watching this right now that I've never met. I know nothing about, but they have that right and responsibility. And it's dynamic. Every epoch, every 5 days, those distributions change. Some make blocks, some no longer make blocks. Some get retired, some new entrants come and so forth. So it's a dynamic quorum. And it's parameterized that as the value of ADA goes up, you get more and more and more of them over time. Okay, so these are already properties, in my view, that are significantly better from a decentralization viewpoint than proof of work, especially given that, as I mentioned, it's a virtual or synthetic resource. And so what that means is, let's say a particular country bans that asset, like China, and it says, oh, we hate Bitcoin now, mining is gone. Well, the problem with ASICs is when you optimize them, they're in data centers. They're very expensive and difficult to move from one place to another. There was a mine that had a problem and the hash rate plummeted as a consequence. A synthetic resource, its jurisdiction can be relocated with the click of a mouse. You basically move it to an address and hold those private keys and operate those servers somewhere else. So if there's a problem in Switzerland, you go to Liechtenstein. A problem in Liechtenstein, you go to Chile, you go to Australia, wherever you want. And you can still be the same individual. You can just move the legal jurisdiction of the hosting infrastructure from one place to another with a turnkey. It might be a slight inconvenience, but it's not a logistical nightmare, and in some cases impossible. And there's no threat of sovereign seizure of these things because it's public key cryptography. Okay, so for those properties alone, I think proof of stake is vastly superior for many of the things that we care about. But for the idea of being able to have multiple synthetic resources, not just one token, but other baskets of things, especially connected to governance or other activities, social benefit inside the system, you end up, in my view, having a significantly more egalitarian system. As for security, security only matters against an adversary. And when he says it's more secure, I'd like to understand what he's actually defining security as. Jack, you can't just say X is more secure than Y. You have to say X is more secure then why, given these assumptions within this model against this type of adversary, and provide some evidence for that particular claim. But again, maximalists don't do this because they're part of a cult. They're not part of a rational thought and dialogue. And that's just where we're at. And when people don't understand a lot about these things, they somehow decide that something's true and they defend it very religiously with very little knowledge to back that. It's an extraordinary thing. Okay. So anyway, I hope this brief video helped you guys. It was a lot of fun to make. I really enjoyed it. Let me go back to StreamYard. There we go. And I wish everybody a good day, and hopefully we can have more conversation in the future about distributed systems. And if you guys do take those courses, let me know your experiences. At some point, we'll probably create some classes specifically about Auroboros. The other thing is, when we have Omega, I will absolutely make sure that we do a series of lectures on how Ouroboros Omega works. That's really the magnum opus of the entire Ouroboros agenda. We've been, as a collection of scientists and engineers, working our way up to that final paper that really pulls all the stuff together. It's the Lebowski. It's like the rug, really ties the room together. And we think that's going to be just the perfect way of doing proof of stake for a very long period of time. And you can really focus on layer 2 stuff as opposed to optimizing the base layer. Okay. Thanks, everyone. This was a lot of fun. Cheers.